All right, this is our lecture for Wednesday in the first week of the semester. And we are going to give you an introduction into a variety of things, code-related things, talk about the design process and some structural components. When we look at structural design, you have been already through statics and strength of materials, and you have been through structural analysis. At least you should have been. Where this course actually fits in is we will start talking about the process of determining structural loads that are applied to members and to structures in order to actually do the analysis, which you've already done, and to come up with the proper sizing and selection of members. When we talk about structural design, that's really what we're talking about, is the proper selection, the proper sizing of members. Members have to be properly sized so that they can transmit loads through them and ultimately in a load path down to the ground. When you talk about structural engineering, you're actually talking about both the analysis and design. And like I said, you've already had a course in structural analysis, so you've learned about techniques that you can use. We'll also talk about a few techniques in the course, especially towards the end of the. When you look at the design process, there's a lot of different facets of design. You can start design with literally an idea or a concept or even a sketch on the back of a napkin. It moves through many phases. It moves through an architectural planning phase, again, where sketches become a little bit more than just the concept. And you start with rough drawings, space layout. There has to be a consideration of various alternatives. What's best for the owner, what's best for the client, what's the most cost effective, what is really best for the owner and the client involved. Ultimately, as information becomes more forthcoming and more refined, your design will become more refined. So essentially, when we talk about design, there's a number of phases, but it basically moves from concept into maybe a schematic phase, ultimately into the development of construction documents. So that's number of we go through. Um, where do we get guidance on this? We absolutely have to have guidance on how we are to apply loads and what combination of loads do we really need to apply. Again, building codes are a great place to start. The book that we use actually is based on the International Building Code, which we'll talk about how that code actually came into being. Our book and our course is also heavily dependent upon a document that we'll refer to as ASCE7 document, which is the title you can see there on the screen. But there's others. The IBC gains a lot of its information from ASCE7. ASCE7 also relies heavily on other references that we'll talk about. When we look at building code development, like I said, it's not like the International Building Code exists just out there on an island all by itself. This particular slide sort of is a graphic illustration of its seismic chapter, and there is an organization called NAHERP, which again did a lot of the groundwork for how seismic loads are actually developed and how seismic loads can actually be analyzed and applied to structures. So NAHRP, what you'll find is that the ASCE7 document really takes a lot of information from the research that NAHRP did over the past couple of decades and has incorporated that. And then what you'll find with the International Building Code, and again we use the 2012 Building Code, that again takes just an enormity of information from ASCE 7. So really there's a reliance of building codes upon other resources, and those resources rely on still yet other resources. And this is sort of just a general concept of how you can see things changing. The International Building Code and the ASCE 7 document came out in 2000. The Building Code came out in 2012, most recent edition. The ASCE 7 document was revised again in 2010. But anyway, what I'm showing you here is a little slide that just has to do with wind loads, wind speeds down in Florida. So I just want to show you what happened in 3 years, from 2007 to 2010. And basically what you see there in sort of red is the 2010 derivation of the Florida Building Code and the wind speeds. And if you look down there at the real tip of the bottom tip of Florida, in red you'll see the 2010 wind speeds, and in black you'll see the 2007 wind speeds. So right down there at the tip, it's real easy to point out that now under the 2010 guidelines, the tip of Florida is supposed to be designed for a wind speed of 150 miles per hour, whereas 3 years earlier the maximum wind speed was 10 mile an hour lower than that, 140. What's happened over these 3 years is that there's been significant changes, because the design level wind speeds are now strength based related. There's also been changes in exposure categories and changes to windborne debris regions, but again, just sort of on the superficial view of things, I mean, you can just see in 3 years how things have changed. When we talk about structural systems, again, you can have a definition as an assemblage of various types of members. Basically, what we're trying to do is create a machine or create a load path where loads are transferred from one member to another member and ultimately down to the foundation and into the soil. Okay? Generally speaking, the most common assemblage of members is a building frame, whether that frame's made out of steel, concrete, wood. There's generally going to be a floor system or a slab system or some sort of diaphragm system where floor loads, roof loads are transmitted to beams, which are transmitted to larger beams, ultimately into columns. And again, this load path works its way ultimately down into the ground. You can classify structures as, in many different ways. Generally, you classify them based on function. We'll be talking about building structures. We'll mention bridges probably in passing, and we might mention a few other things just in passing. But I mean, generally our focus in this semester, in this course, is going to be on building structures. And again, when we talk about building structures, we're talking about structures that are generally occupied by residents, whether that's a house, whether that's an office building, whether that's a school, whether that's a commercial establishment, a hospital. I mean, they're generally going to be buildings or buildings generally are going to be viewed as being occupied in some way, shape, or form. But there's not just buildings. I mean, you could be talking about bridges. I'm sure some of you, as you go on with your studies here, will take a bridge design or a bridge engineering course. There's a whole slew of structures related to highways, which are not bridges, structures that are, drainage structures, culverts, tanks and silos. There are, of course, along with drainage and hydraulics, there's things like dams and reservoirs and detention basins and so on and so forth. But just a whole slew of other types of structures. But for the most part, in here, we'll be sticking with building type structures. When you talk about buildings, you can classify them, again, by their types, whether that's, residential, commercial, industrial, institutional, so on and so forth. But you can really start looking at them in terms of attributes like form, the materials they're made up, height, analysis method, occupancy category, and so on and so forth. Okay. If you look at just form, like I said before, when we think about buildings, most commonly we're thinking about frame structures. We have a floor system that is supported by floor beams, which might frame into girders, which then frame into columns, and so on and so forth. Frames are not just beams. Frames can be made up of trusses as well, rigid frames, space frames, and so on. That's not the only type of building that you have. That's the most common. You can get into buildings that deal with shell type elements, which are plate type elements that again resist vertical or lateral loadings, and so on and so forth. Probably more specialized than what we see 99% of the time, but still can be used for building type. Material, like I said, the conventional materials, steel, concrete, wood, brick, block. You've talked about these in your construction materials course. I know that. And again, it's the building material that things are made out of. We should know the basic properties of the building material, because every building material has its particular strengths and its particular assets that it can give us. Similarly, it also has its weaknesses that we need to know about too. So, but anyway, that's it. If you get into building codes, a lot of times building codes will talk about materials, and they will have specific chapters on materials. But in terms of providing the type of building, a lot of times they'll talk about the combustibility of certain materials as well. We will talk about classification based on height. We'll notice as we get into especially things like wind analysis, or the chapters and the various references that deal with wind and also with seismic forces, that we will have certain methods of analysis which are preferred for low-rise buildings versus high-rise buildings. And again, how they define a low-rise building for a certain type of analysis depends on what that analysis or what that method is. Sometimes, we'll talk as we get into wind, a low-rise building being buildings less than 60 feet. Or high-rise buildings being over 100 feet or 160 feet. But, it really depends on what we're talking about. But we do sort of classify things maybe based again, this depends on a lot of things. One of the things that you should notice is that when people start talking about high-rises, sometimes it's very practical as to why they consider certain heights being high-rise buildings and certain heights not being high-rise buildings. When you think about fire safety, and you think about the reach of a ladder on a typical fire truck, generally speaking, a ladder, the typical ladder, can probably reach a point on a building close to about 100 feet. And therefore, this will affect building codes and fire suppression systems that codes require and so on and so forth. So again, what is really a high-rise building? Is it 60 feet? Is it 70 feet? Is it 75 feet? Is it 100 feet? Is it 160 feet? It will depend on what you're talking about at a particular time. But realize that, in these references, we will look at building heights. One of the things with height of a building that again, just to think about as you go onwards, is that the evolution, the historical evolution of building height, not only in America but around the world. When we had the technology to actually construct tall buildings from a structural point of view, we did not have technologies that would allow us to comfortably live in those tall buildings, or live easily in those tall buildings. I mean, we back in the around 1900, that's when steel buildings started. Tall steel buildings started to become in vogue. But at that time, because elevator systems were relatively archaic, because we didn't have electricity. We did not have electricity and electrical grids until about roughly about 1900. Air conditioning and things like that. That became problematic to have buildings over 10 or 15 stories. So anyway, that's the technological evolution of that played a role in building as well. You've probably we've talked about how about in around 1900 you started getting taller buildings, but again, there were limitations. This is just a list of, actually an old list of tall buildings around the world. This has the Burj Dubai and the United Arab Emirates as being the tallest building. That has since been replaced. But anyway, one thing I'll say about tall buildings is that they sort of go in fits and starts. If you ever do a historical study of sort of the evolution of tall buildings, you'll notice that in like the 1920s, up until about the Depression, basically, early 1930s, there was a real push and real fame given to the tallest building in the United States and the tallest building in the world. And then because of the Depression, because of the wars, tall buildings sort of were on hold for a while. Then back in the 1970s and 80s, it started again. So again, you'll see sort of fits and starts where, where people go through this, can I have the tallest building in the world or the tallest building in a country stage? And again, there's just some different slides on tall buildings, which again, it's, all have since have been. Design method, you might not think of this, but we really have to think about structures and basically how we are going to design them, how we're going to basically analyze them. So again, this is not the United States doing a classification, but if you go to the United Kingdom, I mean, they'll actually have classifications of different types of buildings and how they can be actually designed, whether they're static structures or dynamic structures all the way up. In what you'll see with us as we get into our references again is that basically smaller, simpler, more regular type of structures will allow an engineer to use a design method or even a method to establish loads that is simpler and more straightforward. As buildings become more complex, taller, more irregular, you will find that the references and whatnot that we'll look at actually speak to how these structures need more rigorous and complex sort of analytical procedures to establish loads and to ultimately design. Again, design method for that we'll see. I mean, we'll talk about gravity framing, wind framing, seismic framing, but even in seismic framing, that will sort of change. We'll talk about seismic design categories, and that'll change depending upon, the geographical region or the design category your geographical region falls into. So, designing a structure for earthquakes up in Chicago will be remarkably different than designing a structure and the methods and the loads that you'll have on a structure for earthquakes in Seattle. I mean, there'll be light and day differences. You also hear us talk about use category, and again, this shows up in the building code, but this also shows up in our ASCE 7 document, where we'll talk about the types of structures and how they are used, and we'll talk about them differently. For instance, if we have a structure, let's say a warehouse, where you have one person or two people going into it once a day, 5 days a week, that structure is going to be designed, the loads on that structure will be designed to be smaller than the loads on a hospital in the same region. And the reason being is that the hospital is going to be considered, an essential facility for public safety. In an emergency, a hospital has to be able to function. That warehouse with two people in it is not really going to make much difference to the public safety and security in an emergency. So we will talk about, and you will see a difference in importance factors that are supplied to different facilities. So again, the idea of how they are occupied, how essential they are, is going to make a difference. Occupancy type, again, on this, again, gets to the purposes, but it really gets to the concept of how things are actually occupied. An office building, for instance, is going to have a certain live load applied. We do not look at the number of people, like people all weigh 200 pounds and there's X number of people that are going to exist on a floor. What we do is we look at typically uniform live loads. So instead of trying to represent a classroom full of students based on everybody being 150 pounds and there being 45 students in a classroom, instead that classroom is going to have a uniform live load floor loading. Okay, that is going to be different than the live load floor loading that would exist in a house, and that might be different than the live load floor loading in a theater. So I mean, again, how things are occupied, how our buildings are occupied, how our structures are occupied is going to make a big difference into how loads are actually established. Um, Again, we won't get into too much of this, but you should know that as you get into an actual building code, that they will talk about classification and use groups and whatnot. So you could see here, like if you got into the International Building Code, you know, a use group that they designate as A-1 would be assembly uses with fixed seating intended for the production and viewing of performing arts and motion pictures. Okay, if you go into like an A5 assembly uses for viewing outdoor activities like amusement park structures, bleachers, grandstands, stadiums. So again, they break that down into various use groups. Now again, that's what a building code is going to do. We will work with the International Building Code, but we won't get too much into their occupancy classifications. Instead, we'll look at classifications for like loadings and this is what I was talking about before. Now this is something that we will get into is we will talk about risk categories. And again, you will see this over and over again as we start applying our ASCE 7 reference, and we'll talk about a risk category of a building. So again, this will go from risk category 1 up to risk category 4, with 1 being something that, like I said, like the warehouse where 2 people are occupying 1 time a day for 5 days, all the way up to risk category 4, which will be, again, something that is considered an essential facility. So, that could be something that, either might be like a hospital or a police station or a communication command center, something like that. Here's what I was talking about, how these risk factors, or how our categorization of the type of building we have based on its risk if it was compromised during an emergency. You'll see this as it relates to the different loads that we'll talk about. Again, and we'll get into this more in depth as we progress through the semester. But for instance, like the seismic importance factor. If I have a building that's a very low risk category, the warehouse where nobody's in or 1 person's in, I'm going to give it an importance factor of 1. So I'm going to take my loads and I'm basically going to multiply it by 1, whatever loads are established. If that was a hospital or an essential facility that was in the same geographic location, what would happen is I would apply a importance factor of 1.5. And so any loads that I had established relative to earthquake, the inertial forces caused by an earthquake, are automatically going to get increased by a factor of 50%. Okay, and again, the reason we're doing that is we can't have we tried to design against an essential facility being compromised under a certain event, which would in fact compromise a low risk building. Okay, so that's sort of what we're getting at right there. One of the things that we'll talk about too, especially here in the next few weeks, is we'll talk about load path. Okay, so this is just a little slide that's supposed to again get you thinking about how are loads actually transferred. Okay, And is there any type of redundancy? So here's a simple truss. I've got a load. It's pulling down on a simple truss. I think you'd all say that, hey, we'd like our loads to flow through these truss members and ultimately down into the support. If, you know, something would occur, like a member would break, okay, what would happen? Well, if a member would break like that, um, would the load be able to be transferred anyplace else? In this case, the answer is no, okay, and because it's not able to flow anywhere else, we'd say this is a non-redundant load path. If we had the same truss, but we had some counter diagonals, okay, one would break, there would be the ability for the load to flow through someplace else and ultimately to make it down to the ground. So that's a redundant load path. So we can talk about things based on redundancy as well, and you'll hear that topic come up as we go on to the class. Okay, generally, our basic idea is that we like redundancy. I mean, we like bridges that the bridge deck is carried by 6 steel girders. If one of the steel girders fails, you still have 5 left. Although you might have a localized failure, that one bad steel girder won't bring the bridge down. If you have 2 steel girders that supports a bridge and one of the steel girders fails, well, then you got a different situation because either a substantial chunk of the bridge is going to come down. There's probably not going to be a lot of ability for the transference of load, and that could, again, that could be devastating. So we'll talk about load paths, and this is something that, again, you're going to get, again, some more work on that in this course in this semester. But what we have to be able to see as you progress through your engineering studies is how loads are actually transferred from one member to another. So you can have, over there on the right, like we talked about a lot, you can have a building frame system. Well, building frame system is basically going to take the floor loads or the roof loads, and those will be transferred directly to beams. Okay, now you can call these beams, you can call them stringers, you can call them small beams, whatever. And those smaller beams generally are going to transfer their loads to a larger beam or directly to a column. The larger beam, if they transfer loads to that, is usually called a girder. So again, don't get too caught up in the terminology, beams, girders, stringers, whatever. If you're in bridge engineering versus building engineering, some people will call things different, but by different terms, but it's not a huge deal. But the load path is a huge deal. You have to be able to see where the load path is, and then that's going to be critical in determining the load that you have actually on certain members. If you go to the bearing wall system, which is on the left, I mean, that is, again, a system where, again, your floors or your roof is going to be transferring loads to, again, beams or maybe just directly to the bearing walls. But the bearing walls are going to bear ultimately down either on lower bearing walls or ultimately down to the foundation walls or the footing. So like in the, if you want to call it the first floor has a roof, and again, that might be a rafter or a roof beam or, whatever it is. And those loads on the roof are being transferred to the outside walls, maybe to an inside wall. If it is to the inside wall, that's called a bearing wall. If it is a bearing wall, if it does bear gravity loads, there better be something underneath it that also is capable of taking those loads and transferring them on. And again, just another sort of illustration of that, of a residential system. A lot of people think house residential structures, houses, are actually easy, but they can be pretty complicated, especially their roof framing and whatnot. But again, if you look at that roof truss has to sit where it bears, where we'd say, hey, we saw there's a little pin there when we were doing statics. I mean, there's no pin there in real life, but that truss does bear on a wall. And those loads from that wall are going to have to be transferred to the bearing wall below and ultimately to the foundation system. Okay? There's a lot of different types of load pass. Those were gravity load pass I was talking about on the previous slides, but there's also lateral load pass. What happens when the wind blows on a building, or what happens when I have earthquake forces that are applied to a building? Those are applied laterally. So how are those going to get transferred? How do I take wind loads or earthquake loads, and how do I transfer those on? Okay? Well, there has to be some mechanism for that. Whether it's a moment frame system, we'll talk about that towards the end of the class or the end of the course. Maybe it's some sort of bracing, diagonal bracing that goes on. Maybe it's some sort of concrete or masonry elements like an elevator shaft, a stairwell, whatever, that actually end up being like giant concrete beams, reinforced concrete beams that actually transfer those lateral loads on down. So there has to be, even when you think of wind and earthquake, similarly there has to be lateral load. This is really just sort of showing you like a floor framing plan that again, you probably know this, but maybe you don't. If you look sort of at the top and bottom, you'll notice like the exterior beams between certain columns have like little darkened in triangles on them. Those stand for moment frames. So a moment frame is going to be where a beam is connected into a column, but the connection is a little bit different. It's a little bit more amped up, if you will. It's connected a little bit different, and we'll talk about this as we go onwards in the class. But it's connected in a way that transfers the moment that's on the beam actually into the column. So it's a rigid type of connection, not a flexible type of connection. But anyway, at the top and the bottom, you'll see MF1, MF2. That stands for moment frame. And you can tell moment frames with the little darkened in like triangles at the end. Or that's the notation they use. On the left and the right, okay, you'll actually, in the middle bay, you'll actually see a BF1 and a BF2, a BF1 over there on the right and a BF2 on the left. Those stands for braced frame. So that's a frame that has, maybe it's an X bracing or a diagonal bracing, or maybe it's like what we call chevron bracing. But that's what that stands for. So again, what this is trying to show you is that we can have certain systems that resist lateral loads. Now, the interesting thing about this is that the moment frame is actually working in a manner where the lateral loads would be like applied in a left to right fashion, whereas the brace frames would be sort of resisting lateral loads that were applied in a up or a north to south direction. Okay, so again, we can have buildings that sort of mix systems, especially lateral load resisting systems. Okay, and this is just again an elevation view of again moment frames and so on and so forth. So again, the little triangles are just the little designators that they use to say, hey, there's a moment connection at this point. And here's some, again, the elevation showing some brace frames. Over there on the right, you can see some X bracing. Over there on the left, that's what we call chevron bracing. Okay, and again, that's if you pushed on either one of those frames, left to right, because we've got those diagonals or those chevron braces in there. That's a very rigid type frame. Okay. If we had a shear wall system, again, now you'll notice this frame doesn't, we don't see any of those designators, like for moment frames, or we don't see any diagonals or anything used. What we might have on here is interior to the building, or on some exterior wall. We might have a stairwell. We might have a elevator core, something like that is actually reinforced to actually accept lateral loads and to transfer those lateral loads down to the soil. Okay. Again, when we talk in general, we might talk about something being rigid versus something being flexible. That's sort of just terminology, but when we talk about rigid, we're talking about something that doesn't undergo appreciable deformation. Everything undergoes some deformation, but we're talking about appreciable deformation. But if you have flexible elements, something like a inflatable roof or cable system or things like that, those are more flexible. Okay. Moving on, we can talk about members as whether they're referred to based on how significant they are in design. Most of the building framing that we've been talking about, that's primary framing. When we talk about floor joist, or we talk about floor girders or bridge girders, those are primary structural elements used for the transference of load. There are secondary structural elements that, again, are still structural elements, but we might think about them just because they might not carry direct loads, but provide instead like some bracing resistance for the main members. So again, if we look at, like even bridge beams, you might drive down the highway and you might get stuck in traffic under a steel bridge or under a concrete bridge. And if you look up at a steel bridge, you'll notice that they have this X bracing between the steel girders every so often. Well, that X bracing is made up of angles and plates and maybe some other things. And you might say, boy, I wonder what that really does. Well, that's not a primary structural member, but it still is a structural member because it's supposed to help resist buckling of the primary member, which would in fact be a bad thing. So you do have members like that are used that are important, but they're not primary members. Again, the foundations. This is the spread footings. These are mat footings. This is the below grade. Typically, we think of concrete type structures. It doesn't have to be concrete, but a lot of times we think of concrete. And the foundation is basically what's going to accept the loads from the building and transfer. It's going to be the sort of the last mechanism, if you will, in the transference of loads ultimately into the soil. So again, this is pretty important. Now we're not going to get into foundation design, but again, later on in another couple of years or whatever, you could probably take a foundation design course. And that's that's going to be important. That's the last piece of the transference of the load path. Okay. We've been talking for almost the full time, so I'm going to stop there, and that will be our lecture for today.